So hi, everyone. You can hear me OK? All right. So it's been a really great day, and I have the honor of closing it. So I hope you've all had a lot of coffee, so we can get through this one final hour and then massive party at the bar. So when I was asked to speak, they said, just speak. And then I looked at the schedule to see what I was supposed to be talking about, and it just said Keynote. So I thought, OK, that's sort of licensed to talk about whatever I feel like talking about. And when you get curious about something and you find yourself like 4 hours later and there's like empty glasses around your table and you've been on Wikipedia and you're like, somehow you've learned a new programming language and like a couple characters of Sanskrit or something, and you're like, I don't know how I got from where I started to where I am now. So that's I jumped down one of those rabbit holes recently, and I wanted to share it with all of you. And if you have questions or things you want to talk about, you can tweet them at me at hmason, or if you're a little too shy for that, my email is really easy. Also, h@bit.ly still works. So just to give you the frame of mind with which I'm talking, I build systems like this, systems that process lots and lots of data and try to make them useful to people in really unique and new ways. So this is something we built at Bit.ly called Realtime. And it basically takes everything being shared and clicked on, the content of that, through the entire Bit.ly service, which is a slice of social sharing across Twitter, Facebook, everywhere else. And it lets you query it. So I've done a query here this morning for what are the stories being read statistically disproportionately in the city of Toronto. And these were them. So a horrible accident, lots of construction, and so this guy. So I learned. You guys have a crazy mayor. And if you want to keep up on all of his shenanigans, like apparently each one of these colors is a different story about something crazy this guy has done. So that is a different rabbit hole. And I'd actually like to go back to my country, the United States, and this is 1880. And this is what the 1880 US map looked like. And in 1880, they did a census, and it took 7 years to compile. And so this was a problem. And this was a problem because the population in the United States roughly doubled between 1880 and 1890. And they realized, the Constitution says we get a census every 10 years. It's just not possible to do it in 1890 with so many people. So it's a big data problem, 1890 style. And there were a few things going on right at that time that actually made it possible for there to be a technical solution. So this guy, his name's Herman Hollerith. He was a New Yorker. So he came up with an idea, and he filed a patent. This is back when patents were actually useful. So the art of compiling statistics, filed by Herman Hollerith. You can actually go on Google and actually see his hand drawings of how his machine was going to work. In 1889, the patent was granted, and then he actually built it. His patent was for a machine. The machine was inspired by railway cards. And the cards would let you count things. So if you rode a train in that era, the conductors would come through and make sure you paid, and they had a card they would punch out, and it would say, OK, here's a woman, and she's probably between 40 and 50 years old, and she's wearing a hat. And they would use that card as sort of a memory of who had actually paid on the train. And he got really inspired by this idea, and he built this thing. Right, so this was a machine that counts things. And that was the machine, and here are the cards. It's pretty cool. He actually built this in 1889. And he founded the Tabulating Machine Company. Which is not a growth name, so eventually they changed the name to something a little more easy to grow with. And for the 1890 census, they purpose-built a machine. They actually sent people, like this woman here who's entering data onto the cards, out into the field to use cards, which they then reassembled to count the census. And this is what the cards looked like. So they had little punch holes you would punch in them. And this is the map of how to interpret the card. Like I said, it was a deep rabbit hole. And each of these things meant something very specific for the census. So one of the things that were really interesting about these cards that they were using is that they were exactly the size of US 1887 currency, which apparently looked like this, which is really awesome, actually. And I know we're in Canada, so you guys have currency that looks like this, with like, it's bright blue and kids are playing hockey on it. But for Americans, this looks pretty crazy. And this bill, yeah. So this bill was 20% larger than the current US currency. So it was actually sort of about the size of the Canadian currency. And he decided to make his cards the size of US currency because he happened to get access to a bunch of Treasury Department boxes to carry the cards around in. All right, so the census has been nailed. Punch cards, count everything. Let's zoom forward a bit into the future. So from 1890 to 1906. We get this, and this was the only photo I could find of it. So tabulating machines in the meantime had taken off. It turns out lots of people want to count things, but each machine had to be specifically built for the application it was designed for. So they built a census counting machine. They built a retail counting machine. You would just call them up and say, like, hey, here's my business. These are the things I count. Build me a machine, and they would do that. So in 1906, they actually built a machine that you could reprogram, and you reprogrammed it by moving these jumpers around. And these jumpers were supposedly laid out in the same way the card was laid out. So we go from money to card to jumpers, and now we can count all the things because you can just build one counting machine and you can count whatever thing your business happens to require you count. So nailed it. Let's jump ahead again. Right, 1928. They changed the format of the cards slightly to make them easier to produce and read. So this was the IBM card. This format became standard. Here's one actually in use by a woman named Marie who ran a business in Missouri where she would actually go in and count things for you in your business if you were not technical enough to figure that out, which I thought was pretty cool. These cards were different. They had rectangular punches, which were apparently mechanically a little bit easier to use. You can actually still go buy them on eBay. If anyone is so inclined, they're not that expensive, free shipping. When I was reading about this, it turns out these cards were actually still in use in the US presidential 2000 election and may have led to some issues there. People debating this, though, claim that it was because those machines, which were IBM counting machines, had not been maintained in 40 years. It's crazy. All right, so that was the 20s. This is 1930s, 40 years after the first tabulator machine. So you know how our opening keynote was talking about how people were coding in Python and then Django came along and it was amazing, and now JavaScript is coming along with Meteor and all this other cool stuff. This has all happened in the last 5 years. We're talking 40 years here of progress. We get our first supercomputer. And it was used in the New York World newspaper, which was a newspaper in New York at the time. We still have a couple. In 1931, to refer to a custom-built tabulator, programmable tabulator, that was built specifically for Columbia University. Now, Columbia University actually has a few wonderful web pages about this tabulator, where they simultaneously brag that Herman Hollerith was a graduate. He got a mining degree, and also that they ordered this machine before it was cool. It looked like this. This machine was apparently used until 1959 at Columbia University, which says something else. And just so we have some perspective, this is Times Square in New York in 1933. Right? These are the cars people are driving around. This is what's going on there. And here's Toronto. It looks really different. It was a different world, and yet we've got our reprogrammable supercomputers that can count anything. They can even multiply and divide. So right, okay, next stop, 1959. This is 1959, right? This is culture. We get the IBM 1401. Now this is the first thing that we would all probably call an actual computer. And as a kid, they used to tell me, like, computers used to be the size of a room, and I didn't really understand it. I imagined walking into a computer and, like, lots of blinking LEDs. But this is what they meant. The computer came with lots of modules you could buy. This computer actually worked both on punch cards and on magnetic tape. It had core memory. You could store your programs. It was transistor powered. It cost $2,500 a month. If you actually do the math out, that's about $20,000 a month in our currency. Well, US dollar, well, it's sort of the same today anyway. That's another story as well. They got more orders for this machine in the first 5 weeks than they thought they would get in the lifetime of the product. People were really hungry for this, and it turned out to be useful for all sorts of applications. So payroll, retail, public utility accounting, where you're counting up how many hours of electricity people have used, retail, merchandising. It really enabled a different kind of commerce. And these were all problems where you're counting lots of things. This might be a trend, right? And so I wanted to know how you actually program one of these things. And it turned out the first language it came with was called Fargo. There's actually now a new Node.js project called Fargo. And I don't know, but I hope it's a reference back to this one, not to the movie. It was the 1401, because that was the model number, automatic report generation operation. And Fargo is programmed on punch cards, and the programs look something like this, and there are several phases in which you program it, and those cards get fed in sequentially. And that is a rabbit hole too deep to go down tonight, but if you do want to check it out, I made you a short URL to the PDF and the manual for how you program this thing. It's really funny because in the promotional materials that IBM used for the 1401, it says, oh, it's so easy, your accountants can pick it up immediately. And in mailing lists where I found people who actually worked on the machine talking about it, they said, oh God, we went through the training, 4 weeks later, we still didn't understand it. And eventually, we ended up skipping Fargo and going to RPG, which is a new programming language. And I believe the only programming language that was initially designed to be used on punch cards that is still in use today. And RPG looks like this. So if you picture that Fargo punch card, you can kind of see where it evolved. This code sample is from Wikipedia. But you can start to see the connections between the punch card, Fargo, RPG. So this machine was so complicated, but it still got incredibly wide adoption. In 2006, an artist called Johan Johansson and a collaborator did an interpretive dance of the IBM Automatic 1401 manual. So we've selected an extremely short clip for you here. 4.5 minutes of it is on Vimeo, and the original performance is 35 minutes, and I hear magnificent. So this was big data, right? This is data engineering. So let's jump ahead again, but this time to a time we're all familiar with now, right? So it's 2013, and just to set the cultural context for the world we live in today, I'll refer you to Reddit, source of many beautiful and horrible things on the internet. And one of my favorite Reddit posts of all time, where somebody asked this question: if someone from the 1950s suddenly appeared today, what would be the most difficult thing to explain to them about life today or about the way we live? And the one answer that just nailed this was, I possess a device in my pocket that is capable of accessing the entirety of information known to man. I use it to look at pictures of cats and get in arguments with strangers. This is 2013. But there's something really remarkable that's happening now as well. So I love to use this photo when I talk about social data. So this is President Obama, actually in 2008, out on his campaign trail in Germany. And he's giving a speech, and it's a great shot. It's really energetic. But what I love about this photo is that every single person in the audience has a phone, a camera, a device of some kind. each of these devices is generating data, recording their experience of this event. It's a very social event. And we, as humanity, are generating and gathering more data than we ever have before, collecting all the data. So now we just have to count it. But it's 2013, right? So we're in data engineering utopia. You can count anything you want, process anything you want. So not to spoil it, but we have a lot of tools for this now. One of them is called Hadoop. And this is what you get when you ask for help. This is totally real. My colleague Misha pointed it out to me. To be entirely fair, though, it was fixed in the latest Cloudera distribution. So thank you, guys. But all right, I want to count things. Seriously. So we're starting to see the emergence in practice of a new way of thinking about software engineering, and that's data engineering. So data is engineering is when the design of the system you're building is dependent on the nature of the data that flows through it. And it's not a new idea, as I hope I've demonstrated amply, but it is one that is happening right now for many different reasons. The primary one is that we just have so much data. That the data has started to overwhelm the constraints of the designs of the system that we've been using for these tasks. The second is that it's actually easy to access compute power. I know many of the sponsors here are responsible for that, so thanks again. But I can, in my underwear, spin up a cluster of machines that can do some pretty amazing things. We've been playing a lot with Redshift at Bitly and absolutely adoring it. I spoke at a conference called Science Online for Teens a few months ago, which is a conference designed to get high school students interested in pursuing science careers. And this young woman came up to me after my talk, and she said, "Can I tell you about my science fair project?" And I said, "Of course." And it turns out she had gotten her DNA sequenced and was running all kinds of operations on it in Elastic MapReduce on Amazon's EC2 service. And I asked how she was paying for that, because I was thinking of Bitly scale budgets, and she said, "Oh, my allowance." And that totally blew my mind, right? So a kid with her allowance is sequencing her DNA on Elastic MapReduce, right? So I do believe that I'm a data optimist, and I know that's a hard thing to say when there's so much data pessimism, particularly politically at the moment. But I do believe that data and data systems should give us superpowers. And I have a few examples still to come. But what I mean by that is that they should give us preternatural abilities, that is, the ability to understand things that in our native, naive human condition we would not understand. And so the system I showed you way at the beginning of the talk, real time, lets you see what the world is paying attention to by any criteria you like. So you can find links about food being consumed in Toronto. And by the way, did you guys know you're getting a cronut? It's a big deal from New York, so we're getting over it, I hope. But I really do believe that we are one step away from building a set of products and systems that give us capabilities that are derived from data that we have never had before. And that's why I'm an optimist. We just have to use those things for good. So if you're actually building a data product or data system today, the process looks something like this. And this is how we work at Bitly, where we have a team of extremely distinguished data scientists. You do your research offline. So you say, OK, Hadoop, let's compromise, count some things for me so I can understand the world. But this is not production code. This is not, it doesn't matter to me if it takes 4 hours or 5 hours or 6 hours. As long as it's on the order of hours, it's cool. I want to understand something. Then I want to do some math, that is, build a model that represents something from my data. Then I design the infrastructure for the production environment around that model. And then only finally, at the end, do we design what will actually go into production once we've put data into our first version of infrastructure and seen where it leaks, where it fails. So what this means is that we actually end up writing most things at least 3 times, and often in 3 different technologies. So for the first one, we're running on Hadoop. The second, we're usually using Python. And then the third, Python or possibly Go. We love Go at Bitly as well. Whatever's right for the particular task. So I was looking for a metaphor to explain how this development process feels, and it feels like this. Also cats and cheeseburgers. We end up with a lot of code like this that we end up throwing away. So this is a Mr. Job MapReduce script that is something we ran to calculate something really simple at Bitly. It's really quick to write, so you don't really notice that you're writing a ton of these, but this just gets thrown away. And I think that's a shame. I think the way we design systems should be more holistic. And that's just taking data like this. So this is what we see when somebody clicks on a link. And we're all nerds here, so most of these fields will look very familiar. Just to point a few out, we have user agent at the top. We have some location data. We have the H is the hash or the link that it got clicked on. The host header is which domain. The referrer is Facebook. The URL is kltv.com, and then timestamp and some other fun stuff there. So we use these throwaway scripts to turn this into this. Let me give you a few examples of what this engineering process looks like. And again, I'm talking about Bitly data. So it is the biggest database of human gossip in the world. And that's the best way to think about it. One of the problems we have to solve is what is human? So again, for anyone who lives on the web, it's no surprise that not every request comes from an actual human being clicking on an actual link. And even sometimes the ones that do are not what you might think. So often people will script things to follow links. We have crawlers. We have requests that appear to be from humans that are not actually from humans engaging in social behavior. We want to understand this. So we do a lot of offline research and say, what does it look like when real people click on a link? And it turns out it looks like this. You see a spike of attention and a decay. And this is actually consistent across social networks, across countries. It's a pretty interesting thing. And if any of you are ever building a system to detect what is trending, keep this in mind, because you'll make the naive mistake of thinking it's like a linear increase over time buckets, and that's going to be wrong. So we built that offline, running on our Hadoop cluster, and we said, OK, there's no way we can put that in production, so we're going to train a classifier to be able to do this in real time. We do that with scikit-learn and Python, using our random forest decision tree. That runs on every click in real time. So you click a link, it goes in a queue, it gets classified. Downstream systems decide how they want to use that. And we enrich that piece of data I showed you before with something like this. So OVI is organic versus inorganic, and we give you a count so you can calculate the error margin on the measurement and how likely it is to be human versus non-human. Right. So that's one example. We only had to build it 2 or 3 times. Not so bad. Awesome, in fact. Right, so next problem. We learn a lot about human beings, but monkeys are cuter than human beings most of the time. We want to solve things like, what language is this content in? And the classic approach to doing this is actually a pretty CPU-intensive one. And by language here, I mean spoken language, like English, French, Spanish. You take the labeled content. That means you have a corpus that you've acquired somehow. So maybe you've pulled the European Parliament minutes, which is a common one. We use Google Translate until they blocked us from the API. And you build a classifier, and then you run that classifier on every new page. And that can be a pretty slow process. And it turns out when you get content like this, it doesn't work. So what language is this? So Google's Translate API will tell you it's English. Twitter, it's a tweet on twitter.com. Twitter.com is in English. Some of the characters, even here in the main content, are in English. But it's actually Japanese, because this is written by a Japanese speaker. I don't speak Japanese. I have no idea what it means. So we went instead and found more data. And we found that every time someone makes a request to a link, it includes the language header their browser prefers. And in a pretty sweet hack, instead of using a bunch of SVMs, we now just calculate the entropy of the distribution over the different languages for the browsers requesting a link. And here is that code, and I apologize you can't read it, but many of those lines are comments. It's really short. And that lets us say that this is actually Japanese, even though another system might say it's English. And that means we'll never show it to somebody who speaks English, but we will show it to people who speak Japanese. So I included this example both because it's a lovely example of sometimes something not working the way you think it should work, something simple working way better than something complicated, and also a case in which having more data gets rid of the problem where any individual piece of your data is very low resolution. So one language header from one browser is not necessarily indicative of anything, but when we get enough of them, all of that low quality data put together lets us make a very high quality judgment. So I also wanted to mention it's awesome to work at a company that loves open source. And if you too work on large streams of real-time data where you have thousands of requests per second and need to process them efficiently, we have a project called NSQ that is in Go. We have a project called ForgetTable, which is or Forgettable. It's a database for storing categorical distributions that decay over time naturally. That's built into the data store. It's implemented in Python and in Go. We also have a database called Count Me Maybe for doing probabilistic operations on sets. And that's also in Python and in Go. All right. So there we go. This is my last one. If nothing else, you've learned a lot about Back to the Future in this. So I wanted to talk about what happens next. So we're currently at a place where it is possible to build these large-scale data applications fairly cheaply. Startups like Bitly are doing it effectively and actually building fairly interesting products. But data is still not a first-class citizen of the engineering process. And when you read about software engineering or when you talk about agile development methodology, which we use, it leaves out the research step. And this is also a problem when you're developing new infrastructure. It's not unique to data engineering. But the way we as a community of software engineers think about building these systems needs to expand to include that. And then I really do believe that if we do this well, it'll enable new kinds of awesome products and systems and new metaphors that will make developing these kinds of systems trivial in the way that Django made developing web apps in Python trivial. And that means it'll expand the capability to way more people. And I wanted to close with one of my favorite data products. I actually have no affiliation and have never met the people who made this, but this is Dark Sky. If you have an iPhone, it's Dark Sky is the app, or forecast.io if you have an Android device. And what they do is they take the public US government weather prediction data, they take your current GPS location, and they make a micro forecast for where you are standing right now. So they will tell you things like, it is going to rain in 10 minutes. It's amazing. And it's beautifully designed around the data that it presents to you. And more importantly, in this crowd, it has an API. So you can do even more cool stuff with it. So back to the 1928 currency. You can see a thread of influence on constraints from even before we had computing devices to the way we engineer things today. And I find that totally fascinating. But we need to be willing to recognize those constraints and question the things that have become our defaults and sacrifice them when necessary. And so that's what I'll leave you with today. I think we will have time for questions. And again, I'm Hilary Mason. If you want to get in touch, you can do so here. I'm from New York, and if you love data and engineering and Python, we're having a conference on September 13th in New York called Data Gotham, and you should come. And finally, I'm going to use my position on stage to say thank you to the organizers, volunteers, and everyone who's putting this event together, because you've done a wonderful job. So thank you.
And we certainly do have time for questions, so if somebody would like to approach the mic while... Oh, Jess is getting up there.
And don't feel like you have to constrain your questions to what I talked about here either.
A phrase that I keyed on is you said that data engineering is about constructing the architecture based on the flow of data through the system. I'm contrasting that with flow of data into the system where everything goes into a database forever and we must keep it forever because it's our valuable, precious data. So when you guys do this kind of analysis, do you look at data that's coming in and then just let it flow through and not try to hold on to everything?
So if you can afford to hold on to everything, you should always do that. But at a certain scale, that's no longer really tenable. And also, you have constraints in timeliness. So most of the systems we've built at Bitly are real-time in that we are expected to synchronously return something. But that's very hard when you're running really elaborate analyses. That's actually very hard to do. So we build everything on a very simple metaphor, and that is a stream of data. The streams run through that NSQ system, which is a highly concurrent Go queuing system we built, where each element in the stream is one line of JSON that represents a record of some kind. So the stream of data comes into the queue. We have queue readers that read off the queue and do some processing. There's a data store of some kind, something appropriate to the system, and our ops team doesn't like that we use whatever data store is appropriate to the system. There's definitely a tension there. And then an API layer on the other side, and then perhaps a product layer on top of that. And so when I say the design of the system is dependent on the nature of the data flowing through it, I mean that you will make those decisions about what your queue readers process, what your API layer is, and what your product looks like based on the data that is available to you in volume and what you eventually want to do with it. That said, all of those streams that we see get archived to text files, which get dumped in a Hadoop cluster and in S3. And so Bitly is still at the scale where we can keep every event and then rederive the later analysis if we need to. And I hope that answers the question. Yeah.
I'm selfishly going to ask a question, actually. So
Sure.
I've had the privilege of working with, I think I have to be behind the speaker, but of some people who are designing big data real-time systems where there is actually a hard real-time requirement. And I've seen them when they put on that cat suit and start chasing that cheeseburger in the early stages of the design. And I suppose I shouldn't have been surprised, but I was kind of astonished at how much of that early design relied on intuition, which I think to neophytes, we kind of think that, well, in big data, the whole reason we want to do these computations is to remove the human decision-making process out of the equation. So can you speak to that early process and the balance between intuition and kind of hard fact that you're getting out of your work?
Yeah, I mean, in the design of these kinds of systems and in real-time systems in general, there's... So I'm actually on both sides of this question, which is kind of a difficult thing, in that I'm a data person, and I don't believe you should make a decision if there is data available to support it without consulting that data. At the same time, having just spent 4 years building systems like this at Bitly, you develop a very good intuition for the data. And one of the ways I find questions to ask is to find a place where my observed reality differs from my intuition in some way. Because those are the things, or I just don't know the answer to a question. Some of those questions might be things like, what does iPad usage look like throughout the course of a day? It's a really simple question. The first time I asked it, I didn't know what the answer should be, and in fact, we made a bet, and I ended up buying the beer, because I was wrong, which is a way to motivate a lot of research. But I think if you're too dependent on your intuition, what you're going to find is once you actually turn the thing on at scale, pieces will break. And so you'll have to rebuild them. And eventually you'll converge on that data-driven approach anyway.
Thanks. It's been a really great talk. I'm curious about the cycle that you mentioned a few times. This is really related to that question. If, for example, the data that you want or the question that you have slightly changes after you've built the system, it seems like with the offline design and then online design and then scaling design, that would be really tough to iterate really quickly. And
Yes.
do you have any specific thoughts on ways that we can build tools that make that easier or a faster process or anything along those lines?
So that's a really good point, and is in fact one of the main challenges that I hope we can build better tools to address. So our practice at this point is to make sure every system does one thing simply that is well understood. So each new API becomes a building block on which we can build different things downstream, and it has a single purpose. So we're not trying to build one thing that we might have to change to add something into, because that just gets very complicated. But I really do think there's an opportunity for combining our design of infrastructure with our initial research phase. And then I think there's an opportunity to combine our design of infrastructure to scale with our initial design of infrastructure. And I'm sort of making this up as I go along, but I hope that as we build these tools, we can build this piece, and then eventually they too can join. So we do one development process for these systems, and it is data aware from the beginning to the end and scales nicely. I should also mention that Bitly is fortunate to be at large scale, but not such large scale that we actually have to invent new technology to hold the data. So we have lots of friends in astrophysics and computational biology and fields like that, where they are in fact just struggling to even count. We're one step below that, and I hope to stay there and take advantage of their work.
Hi, thank you very much. My name's Simon, and my question is, if you had one tip for people who are just starting out, let's say they have a small project or a skunkworks project in a company, what is the one quick and dirty tip that you wish you had known when you first started doing this for new projects?
For new data engineering projects, my one quick and dirty tip is just don't take anything for granted. Like, start at level 0 and actually look at the data before you do anything. More often than not, I will talk to engineers who have hit a wall with a project, and they're asking me for advice on a machine learning problem, but it turns out they don't have a machine learning problem. They have a they never looked at their data problem. So it's that, and then if you're building a project that you suspect might have interesting data, make sure you instrument it in a way that means that 3 months later you're not going to be trying to parse Apache logs. Like, instrument it in a nice way. Your future self will thank you for that. Are we out of time?
Yeah, I think at this stage we're going to have to
thank
wrap up, so let's give Hilary a big round of applause.